chapter 6, and we're on thermochemistry, energy flow, and chemical change. The PowerPoints go a little bit more in depth than what I want to cover, and I want to cover essentially all of chapter 6 today in this lecture so that we could review Thursday. I'll have a review session, let's say Monday night, and your exam a week today on 5 and 6. Now, I know you're panicking or whatever. Breathe. There's only really 2 formulas throughout, all right, chapter 6. And there are a little bit more things we can do with it, but due to time constraints and how we're doing this last set of stuff, what I'm going to essentially do here is cut to the most important stuff that we need in chapter 6 that I think we need. Again, it's basically 2 formulas. We'll finish that. I'll assign homework. Thursday, I'll go over any homework from chapter 5 and 6 and talk about what I think is going to be on the exam on Tuesday. So Tuesday the 28th. And then we'll have a review session Monday night if you choose to. And I could go over anything else Monday night for Tuesday. Okay? So there's going to be a little bit more information on the slides than what we're going to cover. You could just ignore that. All right, extra little, cherries on the sundae kind of thing. So chapter 6 deals with thermochemistry. Thermochemistry, the word thermo means heat. Okay, so we're studying heat chemistry, and it's a part of thermodynamics is where thermochemistry comes from, and you'll get a whole chapter on thermodynamics in Gen Chem 2, whoever you end up taking for that. Okay, so what we have to understand is what is heat. All right, so first of all, heat is energy. Okay, right out of the start, heat is energy. And the units that we usually use for heat are calories with a lowercase c, okay, or joules. All right, so we have calories and we have joules. All right, now the calories that we consume, all right, are capital C calories. So this is known as a nutritional calorie. Nutritional. That doesn't look right. It is right though. I don't know, that looked funny to me. Okay, is a nutritional calorie, and what it really is 1,000, okay, 1 nutritional calorie is equal to 1,000 lowercase c calories. So really, a nutritional calorie, okay, is really what we call a kilocalorie. So what we're going to talk about is not nutritional calories that we eat. Now, the heat in food lab, we are going to talk about that. But in this sense, when we mention the word calories, we're talking about this lowercase c calorie. Now, there is a conversion between lowercase c calories and joules. A lowercase c calorie, okay, 1 calorie is equal to 4.184 joules. All right. So calories is usually represented by shorthand 1 cal and joules by a capital J. So heat is energy. All right. So that's the first thing we have to take away here. All right. Now, the next thing we have to take away about this heat and energy is the following. Heat always moves, okay, from high temp to low temp. There needs to be what we call a gradient. There needs to be a difference in temperature for heat to travel. It's a passive transport. We're not going to lose energy. We're just going to transfer it from one end to another. Or one object to another. So heat will always flow from hot to cold. Okay, so, and it'll do so, all right, it'll do so until we level off. So if I have, it's kind of hard here. All right, let's do this. I've got two temperatures, a high temperature and a low temperature, and I put them in contact with each other. This temperature will drop and this temperature will rise until they level off. It'll never go like this. Okay? It'll never go where this all of a sudden becomes a high temperature. I need a gradient to have a transfer of energy. So, the reason if you pick up a snowball or you pick up a ice cube or you pick up something cold, that your hand starts to hurt after a certain amount of time, it's telling you you're an idiot, let it go, you are damaging your hand. Same thing as if you put it on something hot. Okay? What has to happen is you touch something hot, the nerve signals have to send from the hand to the brain. The brain has to tell the hand that that's hot and you're doing damage and pull it off. And the same thing happens with cold. But the reason you're feeling it is that the transfer of the energy is going from either the hot stove to your hand and burning it, or your heat is leaving your body and heating up the snowball. Okay? So, we're losing heat or gaining heat during this process. An object is always losing heat and something is always gaining the heat until they level off. Energy is not being lost. Energy is being conserved. The heat then changes the temperature. The difference between temperature and heat, as we talked in chapter 1, heat is an actual measurement of energy flow. Temperature is just how hot or cold something is relevant to something else. It's just a measurement of that heat flow. Okay, so heat flow causes a raise or lower in temperature. So I always said, the thing I find out, my wife, when we sleep, if she gets cold, she sticks her, legs and her dead hands underneath me, which they're ice cold. And I always complain, and she said I signed this mysterious contract that comes up at certain times that I don't remember ever signing. But anyway, the physics and chemistry behind that is the fact that the heat from my body is essentially going and, warming the person up or warming her up in general. Okay? So that's the same principle that's happening if you hold a snowball. All right? You hold a snowball, the heat is leaving your body. At some point, human conditions, your body drops to a temperature because your hand is going to get, the temperature of your hand is going to lower, the temperature of the snowball is going to go up. At some point, you're going to reach a critical point that you're going to start doing damage to your hand. Your hand's going to start to hurt to warn you you're doing damage. Drop the cold object. Okay? So, when we're looking at heat flow, it's important to designate two parts. Okay? I have the system, which is anything that I am concerned about losing and gaining heat or energy. And I also have, well, that works beautifully. This is the one that's almost dead. I have the surroundings. Okay? So, two things could happen here. All right? We could have two things happen here. We could have heat leaving the system, or we could have heat coming into the system. Now, the shorthand letter that's used for heat is Q. Q means heat. Everything we study about Q is what happens to the system. Okay? In this scenario over here, the system is losing heat. Therefore, we write it as negative Q. And over here, heat is coming in. We call that a positive Q. At the same time, the heat that the system is losing, the surroundings is gaining. And here where the heat is coming in, the surroundings is losing. Now, I can't stress this enough. Negative Q and positive Q. Positive and negative mean direction. It doesn't mean below zero. So if I look up something and it tells me the system has negative 300 joules of energy, okay? If it says that, that just means that my system is losing 300 joules of energy. So if you were asked what is greater, a positive 300 joules or a negative 300 joules, they're the same. They're the same amount of energy. It just means that this one is gaining by the system and this one is losing by the system. Or lost by the system, I should say. Okay. So it's very important to distinguish what's the system. Usually the system is a chemical reaction. But if we're talking the hand and the snowball situation, if you say your hand is the system, then the snowball and the air around and everything else, okay, is the surroundings. So my hand is losing heat, the snowball is gaining heat, and so is the surroundings. So how do we calculate Q then? Okay. Well, there's multiple ways, but the one way we're going to talk about is this one right here. All right, here's our first formula. Q equals M times C, okay, times change in temperature. This is known as the mass, of course. This is known as the specific heat. We'll talk about that in 1 second. And this is essentially TF minus TI change in temperature. The specific heat of a substance is the amount of heat required to raise 1 gram of that substance 1 degree Celsius. Okay? And each substance has its own specific heat. Okay? So let's make up an arbitrary problem to show how this formula works. It's really easy, guys. It's plug and chug. Just make sure you know your units of your specific heat, because that's going to dictate what your temp needs to be in and what your mass needs to be in. So let's say we had an object, okay? And we were told that the object's specific heat is 0.89 grams grams degrees Celsius. Okay. It's joules, grams, degrees Celsius. Sorry. Joules, grams, degrees Celsius. Okay. And I said to you that the object's mass was 0.12 grams. And the initial temperature was 100 degrees Celsius. and the final temperature is 30 degrees Celsius, and I want to know what Q is. All it is plug and chug, guys. So Q equals the mass, 0.12 grams, times the specific heat, 0.89, 9 joules, grams, degrees Celsius, times the change in temperature, which would be 100. Okay, final minus initial. All right, 30 minus 100. Okay. Now we would do the math. Now my answer should be negative because I am losing heat. How do I know I'm losing heat? I was initially 100, now I'm 30. And I get negative 7.48, negative 7.5 joules of energy was lost by this object, whatever this object is. And the thing about the formula is, as long as you're given, so there's 1, 2, 3, 4, 5 variables, if we count TF and TI as two different variables, specific heat, mass, and Q. As long as I'm given 4 of the 5 variables, I could calculate the other. If I was given Q, C, TF, and TI, I could find mass. If I was given Q, M, TF, and TI, I could find C. If I was given Q, M, C, and TF, I could find TI doing the algebra. Okay. Questions on this? So we just looked at Q calculating for just a random object sitting somewhere. Okay, imagine now, this is going to be my awesome drawings. That's terrible. I'm just going to, there we go. Let's do that. All right, I've got a pot of soup, or a bowl of soup, it doesn't matter. Okay, and the soup is hot. Okay, let's say the soup is boiling. So the soup is, or water for that matter, is 100 degrees Celsius. Okay. And I've got 100 milliliters. Yeah, let's make it 500 milliliters of the 100 degree Celsius soup. Now, I want to eat the soup, but it's too hot. So maybe mom, dad, grandma, aunt, uncle, whoever used to drop some used to put some ice cubes in the soup. Okay, and let's say they put in 10 grams of ice cubes, and the ice cubes are at 0 degrees Celsius. Okay, so the total mass of the ice cubes is 10 grams. And I want to know what's going to happen, okay, during this process. Okay, what's going to happen? So what's going to happen if I have 100 degrees Celsius soup or water, and I put in 10 grams of ice cubes at 0 degrees Celsius. So now I don't want to know the math. I just want to know in general what should happen. The soup will cool down, and what else will happen? The soup will cool down, we eat the soup. The soup will cool down. Okay, so this should drop, but what else should happen? If that drops, since we can't have a loss or gain of energy, what else should happen? The ice's temperature should go up. And this is why the ice melts. So what's happening is that heat is transferring from the soup to the ice. So, in terms of Q, the soup is losing energy. And the ice is gaining energy. You got it. So, there is one key factor here that wasn't mentioned. What about the bowl? Well, we're going to assume we're using a thermos or a negligible heat loss gain, which we now call heat capacity container. So we're in a styrofoam container, or we're in a thermos, so that all of the heat that's transferred, we're going to assume goes from the soup to the ice cubes. Which means whatever the soup loses, the ice gains. And here's the formula. The negative Q of the soup is equal to the positive Q of the ice. Now, after you draw the picture and after you understand, that's when you attack this formula. Now listen to me. Listen good here, and then you'll never have to worry about anything. It's important that you know which one's negative, which one's gaining, and which one's losing. The negative is the losing, the ice is the gaining, and here's why. I want to know the final temperature. I'm going to use that MC delta T. So I have 500 mils. That's 500 grams if we're dealing with water, and soup is basically water. We're going to assume that in this case. Okay? Using the density of water, which is roughly 1, 500 mils is 500 grams, give or take. Okay? So, MC delta T. M times C times the change in temperature. But here's the important part. If I'm setting something up like this, if I'm negative Q, okay, if I'm negative Q, delta T becomes Ti minus Tf. Make a note of that. That's important. If I'm positive Q, it's M times C times Tf minus Ti like it normally is. So the negative Q, okay, delta T in this type of problem becomes Ti minus Tf. Every other time, if it's by itself, we do Tf minus Ti. But in this situation, when setting them equal, do Ti minus Tf. The whole thing is you're multiplying that negative out throughout the whole entire thing. But we don't have to worry about the math if you just remember that little caveat. So, 500 grams. Now, C we would have to look up for water. C for water is 4.184. It's that conversion that gets us from joules to calories. Degrees Celsius. The initial temperature is 100 degrees Celsius. I don't know what TF is. Over here, the mass is 10 grams for the ice. Okay, mass is 10 grams for the ice. Since it's ice, it's still 4.184. And then we're going to multiply that by TF minus TI. I don't know what TF is. I know that T initial is 10 degrees Celsius. Okay, everybody with me so far or no? Everybody with me where I got the numbers and all of that? This you'd have to look up or be given. This was given in the problem as milliliters. I converted to grams. Given. This is the big key to this problem. The negative becomes Ti minus Tf. But before I go on and do the math here, do I have any questions? All right, so I'm going to multiply and distribute. Okay. So 500 times 4.184 times 100 is 209,200 minus 2,092 TF. And that's going to equal, I'm going to take 10 times 4.184, which is obviously 41.84 times, this was 0 degrees Celsius, not 10 degrees Celsius. 0 degrees because it was ice. Okay, so I'm going to have that equal, distribute 10 times 41.84, or 4.184, which is 41.84. Multiplied by TF is TF times 0 there. Okay. So I end up with an equation that looks like this. Okay. I'm going to add and isolate my TF to both sides. And I get that my final temperature should be roughly 98 degrees Celsius. So the 10 grams of ice just lowered my amount 2 degrees Celsius. So it's probably still too hot to eat. Okay. So how did I get this again? Multiply, distribute, multiply, distribute, multiply, distribute, multiply, distribute. It's 0. This times that is 0. The number, you could double check yourself, should fall between 0 and 100 because the ice should be moving up and the temperature of the soup should be moving down. It gets a little bit more complicated if I'm not in a negligible heat system. If I'm in a negligible heat system, I could regard or disregard the bowl or container. So what I need you to do is do some of the homework where it is negligible heat loss or an insulated container. And then on Thursday, we'll talk about what you'll do in lab or what you would have done in lab and how we have to take into account the container. But I need you to be able to do these type of problems before we even take into account the container. It's just adding an extra step, an extra variable in there. It's not difficult. It's just a little bit longer algebra. But I want you to try these first. So is there any questions on solving Q-type problems? Or where I got a number from, or how I did this, or anything like that? You have to look that up, Trenton. That is the specific heat of water. So you'd either be given that in the problem, or they tell you like you have water and you'd go to a table and look up the specific heat. All right, then. So I'll give you some homework problems on that to try. And then we will now look at... Microphone keeps popping off here. All right. Let's look at another term. Now, there's a term called enthalpy. And it's represented by H. Okay? And you'll see a little HF, or you'll see a little degree sign with H. This means formation. This means at 298 Kelvin and 1 ATM. Okay? Now, if I keep my pressure and volume constant, H equals Q. H is known as a state function. Enthalpy is known as a state function. And what that means is I'm not worried about the path I took to get where I'm going. I'm just worried about what did I start with, where I ended up. Okay? And what I mean by that is, okay, if I were to measure, I have ice, okay, and I want to measure the enthalpy of turning it into vapor. I would just worry about the change in, and delta means change in enthalpy from ice to water vapor. If I were measuring it in Q, that's a state function. I'm worried about where I started and where I ended. If I were looking at Q, I'd have to go ice to liquid to vapor. And look at the change in Q. So this would have had a gain energy, this would have had a gain energy, as opposed to just looking at ice to vapor. But the good news is that under constant pressure and volume, and for our point right now, we're going to run our experiments at the same pressure and volume. Enthalpy is equal to Q, which means the positive and negative thing means the exact same. Gaining heat, losing heat. Gaining enthalpy, losing enthalpy, positive and negative. Well, if we look at enthalpy, there's something called Hess's law. And there's two parts to Hess's law. One, you're going to be able to use your book. You're going to need Appendix B. If you don't have a book, I'll post Appendix B on Blackboard if I didn't already, but I think I might have. But if I didn't, I'll have Appendix B up on Blackboard. But here's the first part. Okay? Hess's law basically says that if I know the enthalpy of reactions that make up a new reaction, I could add their enthalpies together. So what I mean is this. Let's say I had A gas plus B gas yields C gas. Okay? And I had D gas breaks down into C gas. Okay? And I want to know A plus B plus D yields 2C gas. So let's say I knew the delta H of this one was 100 kilojoules. I know that the delta H of this one is negative 200 kilojoules. And I want to know what is the delta H of this reaction down here. Okay? Well, if you don't realize it, all I'm doing is adding these two reactions together. A, B, D. We're doing algebra. We're adding two equations together. So if I add A plus B yields C to D yields C, I would get this out down here. Hess's law says then add these two together. Therefore, this delta H must be a negative 100 kilojoules. All right? That's the principle of Hess's law. Sounds really simple, and it is, except here's what happens sometimes. And you should take notes on this of these rules for Hess's law. Okay? So let's say I have the following reaction. 2A gas plus 4B gas yields 2C gas plus 2D gas. And they tell us the delta H for this reaction is 100 kilojoules. Okay? So there's that one. Then they have one over here that says E gas decomposes to D gas. Okay. And the delta H is negative 300 kilojoules. Okay, and let's say they have one more down here that E gas yields 2F gas. All right, let's make it 4E gas. Yields 2F gas. Okay, and the delta H, and again, I'm just making stuff up here, is 150 kilojoules. Okay, and the reaction they want us to find the reaction of A gas plus 2B gas yields C gas plus F gas. And they want us to find the delta H. Now, here's the deal. The first one I showed you, okay, everything lined up and we were good to go and we just added everything up. Yep, you should have specific heat lists in the book. In the back of the book they should be. Or you could just Google, hey, specific heat of alum or whatever, or aluminum or zinc or whatever, and it'll pop right up. But Appendix B should be in the back of your book. Okay. Also. All right. So, here's the deal. This is known as the reference equation, the equation I want. These are the equations that are going to make it up. Okay? My first step, okay, is make sure everything is on the proper side. Okay? Well, A is on the proper side, B is on the proper side, C is on the proper side, and F is on the proper side. So far, so good. But there is a problem. I have a D here. I've got a couple of E's, all right, on the same side and another D there. And there's no E or D down here. So I need the D's to cancel out. Okay? Now, how do I cancel out in algebra? If they're on opposite sides of the equation, they'll cancel out. So to do this, the first thing I want to do is flip this equation. I can't flip this one, but hopefully the D's will cancel out because that'll screw all this up. And I can't flip this one because that'll screw this up from where I want it to be. So I'm going to flip this and rewrite it as D gas yields E gas. Now, write this down. When I flip, my delta H becomes a positive. Okay? Flipping the equation, delta H becomes a positive. Or a negative. It becomes the opposite sign. So flipping delta H becomes the opposite sign. My next step, make sure I'm in the correct ratio. I've got 1A here. I've got 2 up here. I've got to get rid of that 2. How do I get rid of that 2? I multiply everything by a half. This becomes 1. This becomes 2. This becomes a 1. This becomes a 1. Whatever I multiply my equation by, my delta H also gets multiplied by. So this becomes 50 kilojoules. Let's look down here. I've got, I wanted to make this a 2E. I don't know why I made it a 4E. Let's just make it a 2. I wanted to make it a 2. So make this a 2, guys. All right. I want this to cancel out here. I need 1F. I've got 2. Multiply by a half. Okay. This becomes a 1. This becomes a 1. And by doing so, I half this over here. And this becomes plus 75 kilojoules. Now, our last step is, after we do that, cancel out anything I can. I've got a D over here, and I've got D over there. That's gone. I've got an E here and an E here. What do I have left? 1A, 2 B's, 1 C, 1 F. What do I have down here? 1A, 2 B's, 1 C, 1 F. I'm good to go. Now, last step, add these together. 350 plus 75. My answer should be 400 and... well, if we can get this to right. My answer should be 425 kilojoules, and it should be a positive. The thing with this one is it takes practice. You need to try these. Okay, but here's your rules. First of all, make sure everything's on the correct side. If not, flip the equation. If you flip the equation, the sign changes. Next, make sure you're in your right ratio. If you're not, multiply the equation. Whatever you multiply the equation, do the same to the delta H. Last, or second to last, cancel everything out that can get canceled out. Hopefully you're left with what you need. Then add the delta H's together. And there's homework on this that I'm going to give you for you to try. And the best way to do it is try it. Try it, try it, try it, try it. It's a technique. It's like figuring out a puzzle. All right, questions on this? We have one more thing to do, and we're basically done with Chapter 6 in less than an hour. Nothing? Bueller? Did we pass out? Hey, I'm okay with it. If you guys are okay, then I'm going to... This is the easier part of Hess's Law right now. Okay, watch this one. You're going to love this one. This one takes practice, and I'll give you enough practice to get it down. And I'll post the worksheet online also. Okay, on Hess's Law stuff. But, here's one for you. This is... You're going to love it. Trust me. Here we go. I'm giving you this equation. Okay. Let's do C2H6 gas plus O2 gas. So this is known as a combustion reaction, burning in air. It always should have a negative delta H. It should always be giving off heat. They're exothermic. If you don't believe me, next time you're allowed to drive in your car, put your hand on the engine afterwards. Don't complain to me if you burn yourself, but you're silly enough to listen to me to do that. All right, so this is what a combustion reaction looks like. the products are always CO2 of a complete combustion and water vapor. Now, first step you're given this. I want to know the delta H of formation of this reaction. All right? And we can use this to do stoichiometry and all of this stuff. If we were time permitted, we would do it a little bit more, but you're going to do this again in Gen Chem 2 with thermodynamics, so I'm not really concerned. I'd rather get the technique down and then worry about the stoichiometry when we hit Gen Chem 2. But here's what we got. First thing to find the delta H of this is make sure this equation's balanced. All right, so let's try a 2 there because we need 2 carbons. I've got 6 hydrogens. I need a 3 there. All right, so then I need 2 times 2 is 4. 3 is 1. 3, so 3 and 4 is 7. 7 halves. So we're going to have to double everything. So balancing it out. If I balance it out correctly, it should be this. Okay, number 1 step, balance it out. Okay. Okay. So let's double check. 4, we're good there. 12, we're good there. 14, 4 times 2 is 6. Nope, I'm off. 4 times 2 is 8. I add them. 8 and 6 is 14. So we're good. All right, here's how you find delta H with an equation where I just have one equation and I'm not trying to use multiple equations. The formula is this. The delta H of the reaction is equal to the sum of the delta H's of the products times their coefficients minus the sum of the delta H of the reactants times their coefficients. So this is why it's important you balance the equation. So I'm going to write it here. Balance, 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 balance. Okay, so if I were setting this up to find the delta H, products minus reactants, it would look like the following. Okay? It would be 4 times the delta H of CO2 gas plus 6 times the delta H of H2O gas. Now, I can't stress this enough. States of matter matter. The value of the delta H of CO2 gas is going to be different than if it was a liquid or a solid. Okay? The value for gaseous water or water vapor is going to be more, or different, I should say, than that of a liquid or a solid. So states of matter matter. Don't lose those. Okay, and we're going to subtract that from, and I'm going to write it down here, my reactants. 2 times the delta H of C2H6 gas plus 7 times the delta H of O2 gas. All right, this is how it would look. And I would do the math. So where do these values come from? Where do I get this, 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 and this? Where does these values come from? And where these values come from, we'll go like that, is Appendix B in the back of your book. If you look at Appendix B in the back of your book, there is a whole list of delta H's for specific compounds. The thing is, number 1, balance your equation. Number 2, states of matter matter. Okay? So to solve this, I would just look up CO2 gas is delta H, plug it in. H2O gas is delta H, plug it in. C2H6s, plug it in. O2s, plug it in, and then do the math. I will post Hess's Law problems online in addition to what I'm going to assign you now for homework. Okay. Questions? Uh-oh, this one's done. Homework on Chapter 6. Again, the slides reiterate this. The slides go into a little bit more stuff, things like that. 6.37 to 6.44. 6.37 to 6.44. And this is page 289. Page 290, 6.57 and 6.58. .70 to 73. Page 291. 6.76. The key to 6.76, they give you a reference equation. They give you 4 equations. Okay? You don't need to use all 4 reference equations in that one. That's the hint. And then 6.82 to 6. 8.2 and 8.3. 6.82 and 6.83. Okay, so 6.37 to 6.44. 6.5758, 70 to 73, 76, 82, 83. They're grouped in pairs, so if you could do one, you could do them all. And then more Hess's Law on Blackboard. I'm thinking exam April 28th, which is next Tuesday. Okay, so on 5 and 6. We'll go over anything you want. We'll use that whole time to go over all this stuff in 6 again if you need to.